All right, so let's, at the pictures at the top, let's label these triangles A, B, C, and then this one A, B, C. And all this picture again is highlighting with the reflection, noting that every point, we can call it a pre-image, or it's the original point, and every point has an image. So when you label the image, so reflecting over the vertical line, here's A prime. You can have more than one prime symbol. It can be double prime, triple prime. But all this is highlighting is that the distance from A to A prime is the same to the line of reflection. So here would be C prime, and here is B prime. Now, in this picture here, what I want to highlight is, again, orientation. So I'm going to say C pick above. So in the original figure, A to B to C is labeled in a clockwise direction. And when you look at the image of that triangle, it's now labeled in a counterclockwise manner. So we're talking about properties that are preserved. So within that checklist, the first one is angle measure. So in these two triangles, is angle A congruent to A prime?
C.
Yes. B is congruent to B prime, and C is congruent to angle C prime. So angle measure is preserved. When they're talking about distance, again, remember, another word for distance is length. So is the length of AB equal to the length of A prime, B prime? And that is true. So together, these are true because you have congruent polygons with a reflection. Parallelism. So we don't have a quadrilateral here, but in the homework, you took a look at a rectangle reflected over the x-axis. Parallelism, again, just means that in a figure, if AB is parallel to CD, then A prime, B prime is parallel to C prime, D prime. Segments that are parallel remain parallel. Okay? So that's true. Betweenness. All betweenness means is that if you have a point that's on a line segment or on your figure, whether it's in the middle or, so we'll take a look at this diagram on the right. If I have a point that either, again, is the midpoint or just between 2 points, on the image it will also remain between. So again, if this point's between A and B, it's also, when I reflect it, between the image of those 2 points. Would we agree? Yeah. So then that brings us to collinearity. So what that's saying is these 3 points that I look at on this side, since I drew that point between, if those points are collinear, then when I reflect, the points still remain collinear, and that's true. And then last, is orientation the same? No, so I don't check that box. Okay? So on the right side, again, properties preserved under a point reflection. If I take a look at this picture again, I just want to highlight that this point from the reading is the midpoint. We talked about going over the homework. I'll call midpoint point M, that P, M, and P prime are collinear. So that means the slope of MP equals the slope of M prime P prime. Now I realize there's no angles here. There's no polygons. So when we talk about angle measure, distance, parallelism, betweenness, collinearity, orientation, if I were to add to this picture in any way and draw some angles, for instance, everything would hold to be true. The letters don't change or rotate at all, so they still stay in this upright, okay? So everything here is more or less checked, okay? P doesn't move at all. It's still facing upright in the same position as the original point. So our first construction, we're going to construct the segment that represents the line of reflection for these two quadrilaterals, one being the image of the other. I just want you to make note that this line of reflection is the perpendicular bisector. So in constructing the line of reflection, I want to first take and draw a line segment that connects any point to its image. So let's connect C to C prime. Then I get out the compass, and I'm going to construct in that segment the perpendicular bisector. Again, you can draw the full arc, or you can just make the X. So I'll draw, just because it's easier for me, to make the full arc using the board compass. And then through these 2 points of intersection, I'm going to take my line tool again and draw the line segment. It just said to draw the segment, so I don't need, again, the arrows. But in talking about the line of reflection, I am going to extend and put the arrows on it. So again, I just want to highlight that this is the perpendicular bisector. Moving to the next page, this time we're going to construct the reflection of that triangle. So when I take and reflect the triangle over the given line, okay, we're going to have its reflection in the space below. Now keep in mind that every point, so I'm going to make 3 dots to start. Every point to this line of reflection is going to be the same distance below. But again, keep in mind that this line was the perpendicular bisector. So the first thing I'm going to do is take my compass and I'm going to construct, here's a point off the line. We're going to construct the line that's perpendicular to that. So that was the second question on your warm-up. So in taking the tool, to not make as many arcs, and I'm going to show you how to make this a little bit easier, the first thing you want to do again is make an arc that intersects the two, or intersects the line of reflection twice. Now you may be able to leave your compass setting the same, but now take the compass point, put it on, again, one of your points of intersection, and then put the pencil, it's the same distance, right? So all I need to do is I'm going to create the perpendicular bisector of that segment that goes from here to here, okay? So I'm going to get rid of that line, and I'm going to make, again, the arc. I have to start over. All right, so I'm going to take and I'm going to make the X here and then below. Put the compass point here now. And I'm going to make the other part of the X. Again, you can make the full-size arcs. So make the X above and below. And there's enough of an intersection. So now at that point, so if this were A, this would be A prime. So we have to do that 3 times. So it's nice when we have a triangle, because if we have any polygon that has a larger number of vertices, we have more perpendicular line constructions. So again, I'm going to open it up, and again, I want the arc to intersect the line. Again, you should be able to keep the compass setting the same, put it on one of your points of intersection, make the X above and below. And here, again, if this was B, this would be B prime. So I'm going to go ahead and do the last one. Now with the last one, if you can make it fit, go ahead and draw it. But what you may need to do is extend the given line. So I'm going to try to see if I can make this one fit. I'll do it in blue. So I need my pencil, again, to intersect. It's not going to intersect yet. I'll open it up. That's going to be close, but I'll make it a little bit bigger so it's different from the green arc. So I make the arc there, and then again putting my compass point there. I make the arc above. See how it goes through the point of the triangle. And below. Again, you can make full circles or arc each time, but it's just a lot of marks. Too many to make you confused or the person grading your paper confused. And I'm going to close. And now I have my last point of intersection, which I'll connect again. If this was C, this would be C prime. I'm going to get out the line tool. You guys can use your straight edge and make a triangle. All right, number 3. We have point A, which is 1, 9. So it's to the left up 9, or to the right of the origin up 9, and that one's to the left down 1. So here's the point left down 1, so negative 7, 1, which is A prime. And up here, 1, 9 is A. I need to write the equation for the line of reflection. We've done this before many times already. All this is, a reflected line is the perpendicular bisector. Okay? So if you kind of sketch an idea of what it looks like, if I were to draw a segment that connects these two, perpendicular bisector has to intersect the line segment in red so that it's perpendicular, but also more importantly, what's that point right there? The midpoint. So the first thing maybe you want to do is find the midpoint. You can do slope first. It has to be perpendicular so the slopes are negative reciprocals. But if I find the midpoint of A prime, that's the average of the x's and the y's. So if I add negative 7 and 1, we get negative 6 over 2. Add the 1 and the 9, we've got 10 over 2. So the midpoint is negative 3, 5. So the coordinates here are negative 3, 5. Slope. So what's the rise and run of this segment here? So slope of A prime, again, change of y over change of x. My y values are 1 and 9, so this is 1 minus 9 over negative 7 minus 1, which is negative 8 over negative 8, which is a positive 1. So my line of reflection has to have a slope of what? The slope's going to be negative 1, good. And through the point, negative 3, 5. So it has to have a slope of negative 1 and through the point negative 3, 5. So again, I've been encouraged you to use the point slope form. It's the quickest. If you want to use y equals mx plus b, you can. But again, y minus y1, which is 5, equals m, negative 1, times x minus x1, which is a negative 3. When you subtract a negative 3, it turns into a positive. So now I just need to solve for y. So y equals negative x minus 3. Again, we're going to add the 5 over. And final answer is going to be y equals negative x plus 2. All right, so at the top of the page, it starts to describe a dilation. A dilation is a transformation that reduces or enlarges a figure, and it's dilated about a point called the center of dilation. Okay. The value of the scale factors, so we've already talked about scale factors with similar polygons. Every figure that's dilated is similar to the original. Okay. So this blank here, it produces a similar figure. So we have to remember, in similar polygons, corresponding angles are congruent and corresponding sides are proportional. Okay? However, if k was 1, the figure remains unchanged and would therefore be congruent. So our scale factor, okay, if it's positive, in between 0 and 1, so it's less than 1, is that going to make the figure larger or smaller? Cody? Smaller. If k is greater than 1, our figure is larger. And when the center of dilation is the origin, only when it's at the origin, with a scale factor of k, we just simply multiply the x by k and the y by k. So number 1, find the constant or scale factor k for the dilation that maps this point onto the next point. You just need to take a look at 2 of your coordinates, say the x. So you can set up an equation, negative 4 times what gives you negative 12. Divide by negative 4 and you'll see k is 3. If you want to double check yourself, you can do the same for the y coordinate. 6 times what gives you 18. Divide by 6 and the scale factor you can see is 3. If it was multiple choice, which this question probably will be, you don't need to show any work. You can also take this x coordinate of negative 12 and do the opposite of multiplication, divide, and you can see you get 3. Okay? 5, under a dilation where the center of dilation is the origin, so that's important to note. The image of A is A prime. What are the coordinates of B prime? The image of B. Under the same dilation, so I need to apply the same dilation, so I need to figure that out. How do I go from A to A prime? Well, let's take, and k is equal to negative 10 divided by negative 2, our scale factor is 5. So do the opposite of multiplication, we can divide. If you want to check yourself, you can also check the y values. Is negative 15 divided by negative 3 also 5? It is. So I need to multiply both these points. So I need to multiply 4 by 5 and 0 by 5 to get b prime of 20, 0. And to utilize the space, because we're going to look at the areas and perimeters of the triangles formed in that dilation in the last one, I want you to actually just take a few minutes and make a little T table over here. Dilation of 3 is your A prime, B prime, C prime. And a dilation of 1/2, what's A double prime, B double prime, C double prime. So take a minute. So in the table, we just found the points or the coordinates for the dilations of 3 and 1/2. Now I want you to take a minute and graph them both. So using a straight edge if you need to. All right, so part A and part B both wanted us to just graph and state the coordinates of those two triangles, but I also want to take a look at, again, the ratio of perimeters and areas because these triangles are similar. So now I want you to take a line, though, and let's add to the picture. Again, the center of dilation is the origin, so take and put your straight edge here And I want you to draw a line straight through A prime, A double prime. And you can notice that all of the points within those images are collinear. It does look like a kite. So now let's look at our similarity ratio. So let's compare, or let's actually just pick two of the triangles to show these relationships exist. So you want to compare the original to the larger one, or the original to the smaller one? Smaller one. So let's take a look at triangle ABC. Again, it's similar to triangle A double prime, B double prime, C double prime. What is the similarity ratio for these two triangles? Look at your scale factor. Scale factor was 1/2. But comparing this one to this one, our similarity ratio is going to be what? Okay, so our similarity ratio for those two triangles is 2 to 1, as the smaller triangle is half of the other. So I want you to take a minute. I'm going to put a T-chart here. I want you to take a look at the area of these two triangles, so go ahead and figure that out, and the perimeter of these two triangles. So what is the area of triangle ABC? Again, we're going to look at the ratio of that to triangle A double prime, B double prime, C double prime, and the perimeter of triangle ABC to the perimeter of triangle A double prime, B double prime, C double prime. From the last unit on similarity, we learned about what was true about the similarity ratio and the ratio of the areas, and the ratio of the perimeters and the similarity ratio. Okay, so we took a minute to, we paused, found the areas, found the perimeters, and those are the ratios. What does the ratio 8 to 2 reduce to? 4 to 1. We said in the previous unit that the ratio of the areas was supposed to be equal to that similarity ratio squared. Is this true? Yes. Now, you may struggle in reducing the ratio of the perimeters, but if you pull out a GCF for 8 and 4, this becomes 4 times 2 plus radical 2, and this becomes 2 times 2 plus radical 2, and those could cancel, and then 4 over 2 reduces to 2 to 1. Does that equal the similarity ratio 2 to 1? It does. All right, on the back side, okay, we're going to dilate, parallelogram math, by a scale factor of 1/2 when the center of dilation, so again, a scale factor of 1/2 is the dilation of 1/2. The center of dilation, though, is -2, -6. So here's the center of dilation. There's a typo. This is supposed to be +4. So we're going to start by taking and drawing all of the lines from the center of dilation through each point in our parallelogram. Because we'll know that our images, they all need to line on those points. So I'm going to take, and Cody mentioned, that I'm going to look at this vertical distance from the center of dilation to M. And what's this distance? The distance is 10. So if I take half of 10, I'm now going to go up how many from here? What's half of 10? 5. So here is M prime. So scale factor, again, is half the distance. Each point is half the distance from the center of dilation. Now, that was easy because that line was at or straight up and down is vertical. And horizontal is also easy. So let's just note, though, that this side of the parallelogram is how many units long? It's 6. We note that in my dilation, the segment remains parallel, but it's going to be half the length. So half of 6 is 3, and it has to be parallel. So here is A prime. Again, we can use distance all the way through, but this is a shorter way. Now, if I look at from M to H, instead of finding the length of that, I'm going to look at slope. This is up 4 over 4. So instead of going up 4 over 4, I'm going to go up half, which is up 2 over 2, and it falls right on the line. So I'm going to get rid of those arrows, and here is H prime. Now again, this is parallel to this. We know this is also going to be 6 units, so over 1, 2, 3. Here's T prime, and we're done. At the bottom of the page, it asks us to construct the center of dilation. All you do with that is take a straight line. So you can get out your straight edge, and you're going to draw a line that goes through each point in its image. So there's A to A prime, B through B prime, and then C through C prime. And then right here would then be your center of dilation. So at the bottom of the page, properties preserved under a dilation. Again, keep in mind, these are going to be similar polygons. So every property of a similar polygon. So let's just go right around the room. Dan, is angle measure preserved? Yes. Similar polygons. Corresponding angles are congruent. Corresponding sides are proportional. Vaughn, how about betweenness? Is that preserved? No. Recall that betweenness just means if there's a point on AB, right? So say that point was between A prime, B prime, we'll call that C prime. Does that remain between A and B on the image or vice versa? Yes. Distance. Tanner. No. Distance is also length. And distance is not preserved. Damien? I do already have a C, so let's change that to D. And then the next one, Connor, collinearity. Yeah, so what that's saying is all these points are collinear both on the original and image. So that's true. Parallelism, Jenna. Yes. These segments still remain parallel. And then last, Tyler, orientation. Yes. So again, from A to B to C, that's clockwise. A prime, B prime to C prime, that's clockwise.